Experiment number 6, electrochemistry. There are two parts. In part 1, we will make an electrochemical cell and determine its standard potential and the number of transferred electrons using the Nernst equation. In part 2, we will have a qualitative understanding of the electrohydrolysis of water. This is the diagram of an electrochemical cell made of two electrodes, the zinc electrode and the copper electrode. This is the anode where oxidation happens. This is the cathode where the reduction happens. In these two beakers, we have zinc 2 plus ion and copper 2 plus ion. The nitrate ions are simply spectators. They do not take part in the chemical reaction. Between the anode and the cathode, we need a salt bridge. It's easy to memorize this diagram: A, B, C. A for anode, B for bridge, and C for cathode. We have two half reactions. The oxidation half reaction is this: zinc becomes zinc 2 plus and 2 electrons. This is the reduction half reaction. Copper 2 plus gets 2 electrons and become a neutral copper atom. Overall, the reaction is this: zinc reacts with copper 2 plus and produce zinc 2 plus and copper. 2 electrons are transferred from zinc to copper 2 plus. Over here, this is the reaction quotient. It's simply the concentration of zinc 2 plus divided by copper 2 plus. This is the actual experimental design. We have anode here, we have cathode here, and bridge in the middle. Again, at the anode, the oxidation reaction takes place. Zinc becomes zinc 2 plus and 2 electrons. The oxidation number of zinc increases from 0 to 2. Therefore, it's oxidation. In this experiment, we will use a constant concentration of zinc 2 plus. It's going to be just 1.0 molar. At cathode, we have reduction reaction. Copper 2 plus gets 2 electrons and become copper atom. In this reaction, the oxidation number of copper decreases from 2 to 0. Therefore, it's a reduction reaction. In this experiment, we will use 4 different concentrations of copper 2 plus. We will first use a very low concentration, 0.001 molar copper 2 plus, and measure the potential of the cell. And then we'll measure the potential with 0.01 molar copper 2 plus, followed by 0.1 and 1.0 molar concentration. We need a salt bridge. We can make this salt bridge using 30 milliliters of 1.0 molar KCl. KCl is used to balance the charges in the two beakers. And we need this 0.6 grams of agarose. This is to make a gel. We heat this mixture up to around 50 degrees Celsius. It's going to be a liquid. We pour the liquid into this 3D printed E-cell, and we carve out the hardened gel in the left and right regions, because we need those two regions to contain zinc 2 plus solution and copper 2 plus solution. The gel in the middle region is going to be the salt bridge. So let's look at this picture. Again, we have gel here. It serves as a salt bridge. And then on the left, we have anode. Zinc reacts to become zinc 2 plus and 2 electrons. On the right hand side, you have copper 2 plus getting 2 electrons and become neutral copper. Unfortunately, in this photo, the anode and cathode switch places. So over here, this is anode, this is cathode. We're going to measure the voltage using vernier voltage probe. So these two will be connected to this veneer equipment. And again, at cathode, reduction happens, the oxidation number decreases. At the anode, oxidation happens, the oxidation number increases. In the middle, we have a salt bridge. The salt bridge can help balance the charges here and here. Again, over here we have a constant concentration of zinc 2 plus. It's going to be 1.0 molar. Over here we'll try 4 different concentrations. We start with a very low concentration, 0.001 molar, followed by 0.01 molar, and then 0.1 molar, and finally 1.0 molar copper 2 plus in the end. We will measure all those voltages. So the nearest equation is this. This is the cell potential. This is the standard cell potential. What does this standard mean? Well, if you have both reactant and product with 1 molar standard concentration, we have a standard cell potential. And the cell potential is equal to the standard cell potential minus this term. In this term, 2.303 is actually the natural logarithm of 10. R is the gas constant, T is the temperature. We're going to assume the temperature is roughly 25 degrees Celsius. And we take the logarithm of Q, the reaction quotient. The base is 10, divided by NF. N is the number of transferred electrons. F is the Faraday constant. The value of the Faraday constant is this, 96485 coulombs per mole. This is actually the total charge of 1 mole electrons. And we can simplify this equation by replacing R with 8.314, temperature with 298, and we can replace this Faraday constant with this value, and the equation becomes this. The cell potential is equal to the standard cell potential minus 0.0591 times the logarithm of this reaction quotient over N. Again, the base is 10. And now we can measure this Q with 4 different concentrations of copper 2 plus. And then we'll have 4 different reaction quotient, starting from 1000 and then 110 and 1. So why is this 1000? It's just because zinc 2 plus is going to be 1 molar for all 4 trials. But copper 2 plus, well, at first we're going to try a very low concentration of copper 2 plus. It's going to be 0.001 molar, so 1 molar of zinc divided by 0.001 molar of copper 2 plus, that's going to be 1000. So we're going to have 4 data points. And then we can plot this cell potential versus this logarithm of Q. And we know the intercept is going to be the standard cell potential. What about the slope? Actually, the slope is going to be negative 0.0591 divided by N. N is the number of transferred electrons. So somehow, if you can determine the slope, we can determine the number of transferred electrons. So again, I want to show you the equation here. This is the Nernst equation. The cell potential is equal to this standard cell potential minus this term, and this term can be simplified to this. After you plug in all the values, gas constant, room temperature, Faraday constant, and we get this. Remember, we need to plot the cell potential versus the logarithm of Q. This is going to be your y-axis, logarithm of Q is going to be your x-axis or horizontal axis. We're going to do a linear regression and display the equation in the graph. And the slope is going to be negative 0.0591 over N. So you can see over here, this term is negative 0.0591 over N times the logarithm of Q. What about the intercept? Again, the intercept, this is the intercept. The standard cell potential is the intercept. The literature value of the standard cell potential is 1.1 volt. In part 2, we'll do a interesting reaction. We're going to turn water into hydrogen and oxygen. We have to use a battery over here. Usually we use a 9-volt battery. 12-volt battery works better, but it's more expensive, and this experiment is called electrolysis of water or electrohydrolysis of water. We're going to observe two different reactions at two different electrodes. There are two electrodes. At one electrode, hydrogen is produced. At the other electrode, oxygen is produced. And now let's look at these two reactions. With the help of a 9-volt battery, we can observe these two reactions. In the first reaction, water gets electrons to produce the hydrogen gas and hydroxide. And this is basic. It's going to turn a pH indicator violet. And also water can lose electrons and form this hydronium and oxygen gas. At this electrode, the solution is going to turn red. If you remember to add some universal Yamada pH indicator in the solution, it's gonna, so over here this is gonna turn red, this part is gonna turn violet. What about the overall reaction? You just need to sum up these two half cell reactions. I'm gonna just sum up the left hand side and put it here. I'll sum up the right hand side, I'm gonna put it here, and then we can combine 4 water and 2 water. We get 6 water. This 4 electrons and this 4 electrons cancel. So on the right hand side we have hydrogen gas, we have oxygen gas, and also we produce hydroxide over here, and we produce hydronium over here. So that's why you're going to see different colors near the two electrodes. Again, if you added Yamada universal indicator into this beaker, this Yamada universal indicator can turn red at low pH or violet at high pH. By the way, you do need to add this in this experiment. You add potassium nitrate in the beaker. This is to increase the conductivity of water. Otherwise, the reaction will still take place, but at an extremely slow rate.